Okay, so I want to talk briefly about armouring. So remember in the previous lecture I said that the Hallstrom diagram describes water flow velocities that impact which sediments can be mobilised in the flow, the maximum size of particles that are moved with the flow. So for non-cohesive sediments, generally, as the flow velocity increases, then the maximum particle size that can be moved increases, right? And that sort of has a log-log relationship with the velocity, and Hallstrom described that. For cohesive sediments, like clay soils and that sort of thing, as the flow velocity has to increase again to move smaller and smaller particles, because these particles tend to have stronger and stronger bonding to each other. Now, we're going to look at the other end of the scale, right? The larger particles in this case. And we're going to look at what happens on hill slopes when some particles do get moved and what happens to the particles that are left behind. And so what we're going to say is that basically what's left behind is going to be more resistant to erosion because it hasn't been moved by the flow. And that's called armouring. So I'm going to give you a case study. Here's some hill slopes in the Great Sandy Desert. And off in the distance there, you can see a mesa. Right? And a mesa is essentially a hill with a hard rocky cap. And when we look at these hills in a bit closer detail, we can see there's that hard rocky cap. It's actually a rock that has undergone over millions of years some secondary silification. So the silica out here is precipitated out and formed this really hard rocky cap. And underneath this hard rocky caps, typically we find soils below the rock here which are really susceptible to erosion. And that soil that you used in your experiments the other day out under the rainfall simulator actually came from hills exactly like this. And they may have actually come from this hill. Well, I go back and have a look at some of the data about where it came from. But what you can see on these hills is rock that was left behind from this rocky cap. And because even though this soil underneath the rock is highly susceptible to erosion, these hills are millions of years old, essentially because this rock protects the hills from eroding away. So let's have an even closer look at these hills, and you can see there's almost no exposed soil. These hills are just completely covered in rock, particularly on the steeper sections, and in between some vegetation starting to take hold. Now this is an extreme environment, right? This is areas where the mean maximum daily temperature in summer is over 45 degrees Celsius. It's one of the hottest places on the planet. But also it's susceptible to extreme cyclonic rainfall events. So this is in Cyclone Alley in the Pilbara that extends all the way down to Esperance. And in this alley, typically every few years they'll be impacted by really intense rainfall events. So these hills have withstood those rainfall events and show no signs of gullying because they're covered in this rock armour. And mining companies like to use this rock armour as a means to rehabilitate their slopes. And rock's a really good way, in most circumstances, to reduce the amounts of erosion. So we did a study. We were interested in looking at how these rock properties changed with position and how rock content, for example, impacts the likelihood for erosion to occur. And of course, the mining companies are interested in things like how the rock content impacts water availability to vegetation, particularly in arid and semi-arid climates where erosion cannot be based on vegetation alone. So there's a famous diagram which was first presented by Kirkby and Morgan in soil erosion, but it goes back to Abraham's and even a bunch of others that a little bit earlier who suggested similar sorts of relationships. Now, this has been challenged a little bit, but it's kind of interesting anyway. Nonetheless, there's a few of us who still think this is a significant mechanism for understanding the susceptibility of landscapes to erosion. So here we have on the y-axis erosion from 10 metres along 10 degree slopes, right? in micrometers per year. So, log scale here, very low rates, relatively high rates. And here we have mean annual rainfall, right? And what we have here is a bunch of landscapes. So forests, bare soils, grasslands, scrub, and so on, right? And what they find is that typically, this is a composite curve for native sites, right? Which is this dashed line. And we have a look at this composite curve. We find that the erosion rates from these landscapes tends to be highest in some of these landscapes anyway, because these scrubby and bare areas are more representative up here than these forests in terms of frequency of mean annual rainfall. We find that erosion peaks at a mean annual rainfall of about 200 to 400 millimetres, right? And if you have a look at a map of the rainfall for Western Australia, most of Western Australia actually falls within that 200 to 400 millimetre zone, where, according to these guys anyway, there you have the greatest potential for erosion to occur. As the rainfall increases, then actually the erosion potential decreases. And it's kind of weird, right? More rainfall, then the more potential for erosion, but maybe not, because what happens is vegetation takes over. And we have more, and if with higher amounts of rainfall, we can have higher vegetation densities. And so the erosion potential decreases down to a certain point where even with really dense vegetation, forests, for example, they can't protect the soil from erosion, and so erosion increases a little bit again, right, at the higher rainfalls. So think about most of Western Australia sitting up near this peak where we have high rates of potential erosion rates. So Abrahams and his colleagues really do a lot of studies in semi-arid, water-limited environments, particularly Arizona is a good example of where they base a lot of their studies. And they characterise some of the surfaces and erodibility of these sites, and particularly where we have these grasses and shrubby landscapes. And typically what they see is a relatively flat landscapes covered in patches of rock and patches of vegetation. Right? And you have the characteristic sort of microtopography where we have vegetation forming these little mounds, and then in between we have rock covering the surface. And so the combination of vegetation here and rock protects some of these semi-arid areas from significant amounts of erosion because they're forming an armour layer which is protecting the surface. Sometimes that armour layer is called a desert pavement, right? And really, it's thought the desert pavements come about from the conversion of grassland to a shrubland, right? And that's associated with desert pavement formation. So there's some erosion that happens during this conversion, but what gets left behind is rocky material at the soil surface, which is more resilient and more resistant to erosion. The rock fragments accumulate and they reduce erosion rates, prevent erosion. And mining companies are starting to use this desert pavement idea or the rock fragment idea to reduce erosion rates in mine sites. So rock fragments are thought to impact hydrology, right? So hydrology has those direct and indirect impacts on erosion. So rock fragments can, for example, intercept overland flow and lead to increased percolation of water, infiltration of water into the soil. They can reduce soil evaporation. We can lead to accumulation of water underneath the bottoms of rocks due to capillary rise. The rocks themselves can absorb water because they're often, if it's a sandstone or siltstone, the pore space in between is often a lot smaller than the surrounding soils, and so you get absorption of water into the rock fragments. The rocks can lead to ponding of water and enhanced evaporation. So and the rocks can also provide areas where plants can take the water out from underneath them, right? The rocks can intercept rainfall and lead to ponded evaporation. And there's a bunch of other different processes that Poisson and his colleagues describe in their paper in Catena. So it's a little bit debatable. Do rock fragments increase or decrease erosion, right? Or are they good or bad for rock dumps? Because they could potentially reduce the amount of water that gets in. They could definitely decrease overland flow velocities if they're intercepting the water, but potentially they could also concentrate that water into localized areas and lead to locally enhanced erosion rates, right? And increased loss of sediment from the hill. But typically they decrease erosion rates. And here's an experiment that describes just that. Artemi Cerda and his colleagues from Spain did a bunch of experiments with rock fragments on little experimental plots. Experiment 1, experiment 2. They had a certain precipitation rate up near 55 mils an hour. And what we have here is the runoff rate in these little dash points and the sediment concentration during the experiments. So you can see the sediment concentration started off high, right? Initially, because we're losing lots of fine particles. And then throughout the experiment, the sediment concentration decreases, right? Because we've lost all those fine particles. There's armoring going on, self-armoring going on, and there's less particles available for transport. We can also see with the rock fragments, we get lower discharge velocities. In this case here, without rock fragments, they had high discharge velocities, much higher initial sediment concentrations, and the sediment concentrations gradually decreased during the experiment in that case too. Okay. Right, so rock fragments potentially provide an armour against soil loss. They can stop raindrop impact, they can intercept overland flow, they can also act as a mulch, right, decreasing evaporation and potentially increasing plant available water. So Poisson and his colleagues also looked at the relative interrill and rill sediment yields as a function of rock fragment cover. So with small amounts of rock fragment cover, the relative interrill sediment yield was 1, okay, so this is all relative to each soil, but 1 means it's a maximum, 0 means it's non-existent. And as they increased rock fragment cover, they saw a range of behaviours, but generally speaking, decreases in sediment, interrill and rill sediment yield as the rock fragment cover increased from 0% all the way through to 100%. Okay. So if you're going to design a hill slope with rock fragments on it, that's going to resemble a natural landscape. Well, how are rocks organised in natural landscapes? And Simanton and Toy and their colleagues looked at some of these aspects. So they looked at things like rock fragment cover percentage. So that's the percentage of the area that's covered by rock fragments as a function of the local slope, the gradient. Right. They also looked at, these were different hills, right? And generally speaking, these guys found this type of behaviour. So on low slopes, you had low rock fragment cover. On steep slopes, right, you had high rock fragment cover, up near 75%. And that happened across a whole range of different hills, right? It had this general logarithmic relationship. Now, not all hills behave like this. This was from some region. This is from a particular region. You can find different types of relationships in different areas. Right. In this paper from Earth Surface Process and Landforms, they looked at things like the rock fragment abundance, the median rock fragment diameter, and here the median rock fragment diameter as a function of abundance. And so this is from Hawaii, right? So Maui, Hawaii, and some other places, I don't know where they are, Plumas and Chilan. But they found, generally speaking, as the rock fragment abundance increased, then the mean rock fragment diameter increased. As the rock fragment abundance percentage, right, increased, then they found different relationships, and this as a function of elevation. So on some hills, they found the highest rock fragment cover at low elevations, which decreased as you went up the hill. On others, like on the mesas, we would find rock fragment abundance increasing as you moved up the hill. And the mean rock fragment diameter also increased or decreased depending upon which type of hill you're looking at. So it may be important to take that into account if you want your hills to resemble what's going on in the surrounding landscapes. Nearing is another guy who does lots of erosion studies, and he looked at friction factors as a function of rock fragment cover, and he found this friction factor, this Darcy-Weisbach friction factor, is a little bit like the Manning's N that we described in the earlier lectures. So it describes how rough the surface is and how resistant it is to increases in the overland flow velocity. Low rock fragment cover, you have a low friction factor. With high rock fragment cover, you have high friction. Makes sense, right? So that's another mechanism for controlling erosion. And they also found, unlike the other guys, well, a similar relationship to the other guys, right? So as the slope steepened, we had greater rock fragment cover, right? Like we see on the mesas. Right, so rock fragments impact vegetation, and vegetation in turn impacts overland flow and erosion. So let's look at what's going on there. So rock fragments can potentially serve as a mulch. So mulches are applied in agriculture to reduce evaporation rates from bare soil. So rock fragments can do a similar sort of thing. However, rock fragments can also impact the density of the materials, and roots can't grow through rock, but they can grow between the cracks in rock or between the fine particles in between rock particles. Right? So potentially rock fragments can reduce vegetation if they're below the soil surface. And they can impact things like bulk density. So here's an example. Rock fragment, this is again from Poisson, rock fragment percentage as it impacts bulk density in soils. So what we find, for example, a couple of different mixtures, but they found that the bulk density, this is in like kilograms per cubic meter, the bulk density of the material sort of stayed about constant up until about 35% rock content. And then beyond that, the bulk density of the fine earth decreased. Right? This is the bulk density of the material that's in between the rocks. But the bulk density of the total sample, this BDT, gradually increased up until a certain point and then plateaued. Right? And so what we're finding is that as you increase your rock fragment percentage in the soil, you potentially reach a threshold where the bulk density starts to decrease. So what appears to be happening is that below 35%, the fine earth is able to hold up the whole matrix, and the rocks are just sitting in that matrix. Do I have a picture of that? The rock fragments are just sitting in that matrix, isolated from each other. And then we reach this sort of threshold percentage of about 35%, all of a sudden, the rock fragments push on to other rock fragments, and they make the support for the whole soil. And so the fine earth, the finer material which sits between the rock fragments, then doesn't have to support the weight of all the soil above it. And so it doesn't become as compacted or as dense. And so rock fragments can actually reduce the bulk density of the fine earth and make it easier for plants to grow into that material. Here's another example on a different soil showing similar sorts of results, right? And rock fragments have impacts on other soil properties. So they impact, for example, in this case, they impact calcium carbonate content, right? The organic matter content, and the bulk density, which are all going to impact things like infiltration rates, impact how easily plants grow. Organic matter, of course, impacts hydraulic conductivity. And generally, the more organic matter, the higher your hydraulic conductivity. the bulk density is decreasing, and so on, right? So they're going to make it potentially better for plants to grow in. Okay, I'm going to skip on this one. So rock fragments and erosion, right? So let's go to an experiment. Here's your little rainfall trays with a soil on it, some rock fragments that have been very carefully placed on the soil surface. Then we've done some image analysis and looked at quantifying the rock fragment cover percentage and its impact on erosion. And so in your little erosion trace, we were able to establish a relationship between the discharge in cubic meters per second that was coming off your tray and the sediment loss. And this time it's in cubic meters per second. So we're converting the sediment loss into a volume loss from the tray, right? Not just a mass loss, but a volume loss. So with 0% rock fragments, we have high sediment loss, and then only with a little bit of rock fragments, 24%, it ends up being very similar to 46% rock cover. We get a shift in the relationship downwards in the total amount of sediment lost. Okay, and again, Poisson, because he's so prolific with rock fragment covers, rock content and erosion studies. Again, you've sort of seen this plot before anyway, but relative erosion rate and percentage rock fragment cover, generally it decreases down to about 20%, plateaued here, and then continued to decrease a little bit as the rock fragment cover increased again. Now, how do you actually include rocks in a model? Well, Charmin was one of and Cohen were actually some of the first to try and do this in erosion models. And they essentially model this process, right? So you have a soil with rock fragment cover. As the soil erodes, the model selectively removes the fine particles, leaves these rock fragments behind, which are then exposed and can't be moved. And so their model actually tries to predict this armoring effect, right? So they come up with relationships between the erosion rate and the mean particle size, D50, and also rock content greater than 2 mils, and the D50. This is some experimental data. Put that into their model and then look at how the system erodes with time. And I'm going to go into detail. You can look up those papers if you're interested. So just briefly, we were actually interested in trying to understand how the sizes of these rocks come about on these hills. So, for example, from this rocky cap, close to the rocky cap at the top of the hills, we have very large rock fragments. And at the bottom of the hill, we have small rock fragments, right? And if you are sort of familiar now with some of the erosion studies, a lot of people used to think that, well, you get small particles at the bottom of the hill because they are washed down the slope by rainfall events. Well, when we plugged these particle sizes into a Hallstrom type calculation, when we estimated the flow velocities on these hills, we couldn't move these particles, and we could barely move these particles even at the bottom of the hill, right? So how did the small particles get at the bottom of the hill when we keep the large particles at the top of the hill? Well, our idea was a little bit different to some of the others, and we assumed that coming off this rocky cap, we had large particles initially that just broke off. But then over time, these particles broke up into smaller particles due to weathering processes. And then those particles broke up into even smaller particles due to more weathering processes. And while that was happening, because these rocks take so long to weather and break up, the hill slope was actually eroding away. So the fine material in between these rock fragments is gradually dissolved or washed gently down the slope, not forming rills or gullies, but just gradually pushed out from underneath and down the sides of these rock particles. And the rock particles essentially remain in place, falling vertically down and weathering as the hill slope is eroding backwards. So could we reproduce the data with a simple model that described that? And we went out, we took some students, some honours students out up into these sites, and they spent a couple of days collecting hundreds and hundreds of photos of the soil surface and then taking them back to the computer digitizing those images and then drawing rock fragments so we could get their sizes. And in the end, the two students digitized nearly 100,000 individual rock fragments, and we were able to get really amazing data. So what they were able to quantify was the mean diameter of those rocks as a function of distance from the top of the hill, and you can see the mean diameter is decreasing. The percentage cover is decreasing as we move away from the top of the hill. The circularity of those rocks is decreasing, right? So the roundness of the rocks actually get rougher and rougher, less round as we move away from the top of the hill. As a function of mean diameter. So the largest rocks, at the top of the hill are less circular, more angular than the rocks at the bottom of the hill, which are smaller and more rounder, which suggests the weathering process. And also you can have a look at histograms of the circularity, and you can see that the circularity doesn't change too much, only a little bit, as we go down the hill. So we developed a model, and we also compared that model to our empirical data. And the empirical data are these histograms and the little open circles, and the black dots are, the empirical data is the histograms, and the model is the little circular dots here. The initial condition we took to be the size distribution of the rocks at the top of the hill, and we predicted then how the size distribution changed down as we went from the top of the hill down to the bottom, right? So these are three different mesas, mesa 1, 2 and 3, and we take the top of the hill as the model, the initial condition, and then we predict how the rock sizes change as we move down to the bottom of the hill. And the model does really well, fits the data amazingly well. And we were able to then compare the model, which actually describes the breakup of this rock, to a physical model. So we caught up with Arkady Diskin over in engineering, and we came up with a physical model to explain how these rocks break up. And we assumed some sort of stress that was imposed on the rock, either by heat or by water or some other sort of mechanism. But we just chose a heat equation because it was very simple. When you apply a heat flux to the rock, that causes zones of compression and tension within the rock. That leads to a certain probability of failure. And it turns out that our equations for describing how the rocks broke up on the hill actually fitted with the equations that described how rocks should break up depending upon their size, which was really kind of neat. Okay, so anyway, that was just an aside. So in summary, rocks can be advantageous for stabilizing slopes. Rock cover is spatially organized in natural landscapes, right? It has certain characteristics that change with position on the hill. They increase surface friction, they reduce splash, they change the hydrology, and they can be potentially beneficial for plants growing on the sides of hills.